Hello everybody, my name is Jannik and welcome to our presentation about deformation monitoring of the Möhne Gravity Dam in Germany using the persistent scatterer interferometry technique and Sentinel-1 data. Gravity dams fulfill a wide range of functions that reach from security and water management to energy production and touristic purposes. Climate change related extreme events like heat periods and rain events lead to new challenges in terms of observation of gravity dams. However, traditional measurements are expensive and time-intensive. Radar interferometry was already used for monitoring the movements of reservoir dams, but not yet for gravity dams and their huge walls. The requirements for gravity dams and reservoir dams in terms of structure and required accuracy of observation differ significantly. While an observation accuracy of about 10 mm is sufficient for reservoir dams, 2 mm are required for gravity dams. Finally, Sentinel-1 data are freely accessible. These motivations led to a few specific goals for this study. Firstly, we wanted to make use of the PSI technique to monitor deformations at the gravity dam and also make assumptions about the achievable accuracy, especially in comparison with available in situ measurements. In addition, assumptions about the influence of the monitoring frequency on the resulting PS point density were also a goal in this study. For this study, we used the Möhne Gravity Dam as our study area. On the left, you can see the Möhne Lake in North Rhine-Westphalia, Germany, with the Möhne Gravity Dam in its western part. Footprints of Sentinel-1 ascending and descending orbits are shown here, but due to the geometric properties of the wall, we decided to use mainly data from the ascending orbit of Sentinel-1. The used Sentinel-1 data are listed in Table 1. Since the influence of monitoring frequency on the resulting PS point density was of interest, we created 3 different data stacks within the observation period, each containing a different number of Sentinel-1 scenes, as shown in this part. Table 2 lists the in situ measurements which were used for the accuracy assessment. Daily recorded plumb measurements with an accuracy of plus minus 0.5 mm were used. The trigonometric measurements have an accuracy of plus minus 3 mm and are recorded once in 6 months, or with a total number of 27 measuring points across the wall. For the PSI processing, the Gamma software was used. Moving on to the results, this map illustrates the distribution of all 29 computed persistent scatterer points. This is the number which was computed by all 3 data stacks combined, so there are 13 points found in data stack T1, 11 points in T2, and only 5 points in T3. Therefore, the lowest number of points was actually computed by the data stack with the highest number of Sentinel-1 scenes. The PS points are distributed all over the wall, mostly on top of the wall, with a high concentration on the 2 wall towers here in the east and here in the west. These graphs show the deformation profiles of the PSI measurements in comparison with the plumb measurements, which are marked in red, and the trigonometric measurements. 1 PS point out of each stack is shown, so there are 3 graphs. The seasonal cycle of the PSI deformation is very similar to the cycle of the plumb measurements in each graph. The cycle is moving between maximum values of up to 4 mm in March and April of each year, and minus 4 mm in August and September of each year. The trigonometric measurements show more outliers, as can be seen here or here, but this can also be related to the low measuring accuracy of this technique. The similarities between the plumb and PSI measurements are also confirmed by low root mean square error values and high R-squared values in all 3 data sets, as can be seen here. Accuracies regarding the comparison of PSI and trigonometric measurements are significantly lower, which is also confirmed by the given statistical values here and here. In this study, the PSI technique was used at the Gravity Dam in Germany, computing overall 29 PS points using 3 different frequencies of observation. Accuracies of the PSI measurements between 1 and 2 mm were achieved, and especially high consistencies between PSI and plumb measurements were shown. Moreover, a connection between the observation frequency and number of PS points could be made. Possible improvements contain further considerations regarding observation frequency and respective accuracy. Finally, the usage of corner reflectors could improve the visibility and automate the technique on further dams and walls. Thank you very much for your attention.